Thank you all for being here. I'm grateful for the opportunity to contribute to this conversation on the impact of the AI revolution on entrepreneurship. What I really want to do is resolve that AI revolution into 4 distinct perspectives on automated scientific discovery. Each of these perspectives has augmented rather than replaced human inference practices, but each has also reshaped the way in which we conceive the fundamental inference problems in the first place. Those 4 perspectives I have in mind are what we might call GOFI, machine learning, cause and effect or causal learning, and dynamical similarity. I'll run through each of these in turn and leave you with a few parting thoughts. The first of these, GOFI, is, in the words of John Hoagland, inspired by the idea that intelligence as such is made possible by explicit thinking or reasoning, that is, by the rational manipulation of internal symbol structures, what he calls interpreted formal tokens. What unites the collection of methods that usually go under the heading of GOFI is really a shared commitment to this particular model of intelligence. And the central problem, as practitioners conceived it, was to identify the form of the explicit reasoning that human beings use when undertaking or exercising a particular intelligent capacity. The 2 major approaches that evolved from this perspective on intelligence for application of scientific discovery are broadly expert systems and heuristic search. The former is really about compactly representing a set of rules that capture a collection of expert knowledge in a logically compact form. And heuristic search is about something like creative discovery by way of loosely guided search in a space of possible solutions. GOFI has been followed by, and arguably largely eclipsed by, what we refer to as machine learning. Probably the most iconic method in machine learning is the convolutional deep neural network. This is an algorithm designed to find patterns originally in images, but it works just as well for customer data, health data, price data, trading data. This overall schema is the core or the workhorse of so-called deep learning. And it is one particular instance, one particular application of a new set of statistical methods for addressing what machine learning has reconceived as the central inference problem. In machine learning, the fundamental problem is the following. Assume the world presents the phenomena of interest according to some fixed probability distribution. Use a sample of the phenomena to select a model that predicts the feature of interest on the basis of some other features. So, for example, whether or not an email is spam based on textual features, or in a scientific context, whether or not a DNA sequence represents a transcription start site on the basis of its sequential properties. And you want to do this such that the selected model is the best possible approximation of the distribution in the world, and under ideal conditions you can get various sorts of guarantees on at least a certain sort of best. Now, those machine learning methods are enormously powerful and influential. It's not hard to point to, in this room, a number of devices that are effectively implementing those methods for doing all kinds of things aside from email categorization. We use them for things like language translation. We use them as recommendation systems. In scientific contexts, they're being used to identify patterns like, for example, the aforementioned transcription start sites in data that's of such a high dimension that it's very difficult for people to even picture the space of possibilities in their heads. These methods are undeniably powerful methods for prediction, but they don't exhaust the space of scientific inference problems that we want to solve. In particular, they leave out the kind of knowledge that we want to acquire if we want to be able to control a system rather than merely predict a system. The sort of knowledge I'm referring to is causal knowledge. Fundamentally, causal knowledge, what you need to know if you want to control a system, is knowledge about subjunctives or counterfactuals. For example, what would have been the case if things were different? What will be the case if I change the value of some variable x? What do I need to manipulate if I want to achieve some desired outcome? Causal knowledge is the target of what I've loosely grouped together as cause and effect, but you might think of it as the causal learning perspective in artificial intelligence. It is true that correlation is not causation. This is why, in the first place, the results of machine learning algorithms are not supplying us with the sort of knowledge we need for control. But as David Danks is fond of pointing out, correlation is correlated with causation. The causal learning perspective in AI is concerned with using statistics in a different way to extract from our observations this kind of counterfactual knowledge. In other words, the central problem is to learn causal structure, which things in the world make other things happen, right? Change the states of other things, from either experimental manipulation or even, in the extreme case, purely passive observation. As I suggested, there is overlap with machine learning methods in the sense that these are fundamentally statistical techniques, but the conception of the fundamental problem is radically different, and the sort of knowledge that you get out is importantly distinct. This leads us, however, to the last perspective, the newest kid on the block, as it were, that I wanted to bring to your attention. And I call this the dynamical similarity perspective. Identifying unseen patterns, predicting what will be the case, identifying what variable to manipulate to control things, these are all important scientific tasks. These are all important parts of scientific inference. And each of these has been equipped with tools from the aforementioned perspectives. But there's still a whole suite of in some ways more complex inferences, or at the very least distinct inferences, in which scientists engage that require a new set of tools, a new reconception of the fundamental problem. For example, a primary aim of science is to cluster systems into kinds that are governed by laws. Right? You think about science, you think about scientific law. Scientific law refers to a category of things. This is the central problem of the dynamical similarity perspective. How do we learn which systems, be they metabolic processes, animal swarms, trading firms, share a similar causal structure? That is to say, which systems belong to the same law-like or the same kind governed by a common set of scientific laws. And how do we do this using experimental manipulation or, again in the extreme case, passive observation? This actually is a problem that my group works on, and we've developed a number of tools to tackle this and a collection of related problems. In all these cases, our approach treats the system of interest, economic activity for example, like what it is, the behavior of a complex dynamical system. That is to say, a collection of causally interacting variables whose states evolve across time. Our tools have been bundled together into a package that we refer to as Eugene. And at its heart, what Eugene does is compares symmetries. Let me give you a rough idea of what this is. It's a relatively alien concept in the artificial intelligence literature. Broadly speaking, what we call a dynamical symmetry with respect to time is any transformation of a system. So anything, any intervention, anything you can do to change the values of some of the variables of the system according to a fixed function that commutes with the time evolution of the system. Here's a trivial example. Exponential growth of bacteria or bank accounts. A system that's growing exponentially has, as a dynamical symmetry, infinitely many scaling functions. So multiply by 2. It doesn't matter whether I double the population and evolve it through time, or evolve it through time and then double the population, I end up in the same final state of affairs. It turns out that these dynamical symmetries or the collection of dynamical symmetries exhibited by a system, is a powerful way of clustering systems together into categories that are governed by what we would recognize as traditional scientific laws. We've developed a collection of algorithms for doing this in a wide range of contexts, with and without noise, stochastic, non-stochastic. In the interest of time, I just want to give you one small example that suggests what this sort of method can do. So what you're looking at here are traces showing the behavior of 3 different systems over time. Each row represents a different system. Each column represents a different circumstance. So I've treated this as different initial conditions. So perhaps how the system behaves after this system behaves after you've reset it to these initial conditions. And each of these plots is showing you the behavior of 6 variables unfolding over time. If I asked you which of these things is not like the others, it would not be unreasonable to point to the 3rd row, and you'd be correct that the statistics of this trajectory are very different from the statistics of the other 2. And many traditional tools from the machine learning or statistics tool chest would in fact pick this out as a distinct sort of behavior. But this would be to miss what the dynamical similarity approach takes to be the central point. Each of these systems is in fact a Kuramoto phase oscillator system. So you can think of it as 2 variables for each entity, each oscillator, and 3 oscillators per system. These could be fireflies flashing on the bank of a river. They could be electrical circuits varying in voltage. They could be brain waves. What's important is that in system 1 and system 3, those oscillators are causally uncoupled from one another. They independently go about their business. Whereas the middle system here, the one that looks superficially like system 1, is one where there is a causal edge, an interaction amongst all of the oscillators. It's subtle, but it's there. Our methods will assign a distance, what we call a dynamical distance, to each of these systems. And when you run the algorithm on this collection of data, this is what you see. It tells you that the distance between systems 1 and 2 is in fact an order of magnitude bigger than between 1 and 3. Or to put it differently, 1 and 3 are an order of magnitude more dynamically similar than 1 and 2. In other words, we see through the superficial difference in trajectories to the difference in causal structure. What can you do with the tools from this particular perspective on automated discovery? Well, aside from model-free discovery of scientific kinds, categories that will be governed by scientific laws, you can validate complex models. So simulations of arbitrary complexity for which you have no closed-form summary can be compared to the target system in the real world by comparing their dynamical symmetries. You can ask, if I pretend that my simulation really is giving me values from the same set of variables in the real world, do these 2 things have the same or at least similar causal structure? Did I get close to getting the right influence relations? We can detect change. Despite the superficial features of trajectories, we might want to know, has the causal structure altered? Has the ecosystem been changed by human intervention so that the way species interact is no longer the same? And we can even accomplish a novel kind of control. Rather than tell a system exactly what to do, we're able to tell it what kind of a thing it should be and nudge it in that direction while still allowing it to respond to its environment. Let me sum up. One thing I want to stress is that each of the perspectives I've provided is not, or none of them succeeds in being a fully automated process of scientific discovery. In fact, most of them were never intended to be such. These are augmentations, these are tools for carrying out inference processes that human scientists undertake all the time. I think Pat Langley puts it well. He said in a fairly recent paper that although the term computational discovery suggests an automated process, close inspection of the literature reveals that the human developer or user plays an important role in any successful project. Early computational research on scientific discovery downplayed this fact and emphasized the automation aspect, in general keeping with the goals of artificial intelligence at the time. However, the new climate in AI favors systems that advise humans rather than replace them. So what I'm suggesting is that you should understand these 4 perspectives as describing 4 complementary problems and sets of tools for addressing them. I want to stress that Each of these tools has limitations. Machine learning looks for patterns in static probability distributions, but these are patterns of correlation, not causation. I want to stress that more and more of these limitations are being met by novel sets of tools. So for example, the last 30 years have given us a powerful set of tools for augmenting discovery of causal knowledge. I want to suggest that entrepreneurial decision-making process and the economic systems in which they are embedded are dynamical systems. That is to say, they really are at heart immensely complicated causal systems whose states evolve over time. And that suggests that we need to attend to a distinct sort of problem, distinct from the problem addressed by traditional machine learning or even causal discovery tools. And Eugene provides a set of tools for addressing that sort of inference problem, for discovering causal knowledge in dynamical systems. Thank you for your attention.